Good morning, everybody. Quite small group, only 1 week before Christmas. Very warm welcome for today's mixed signal lecture. I have the great honor and pleasure to announce that we have visitors from Singapore today who joined this lecture. This is Dr. Zhu, Dr. Theo and Dr. Kwan from Singapore Polytechnic. I already told you that we have a joint master program in Singapore where we also give this mixed signal course. And now, this year for the first time, there will be a bachelor's program also in Singapore. And this is together with the Singapore Polytechnic. And we have these 3 lecturers here to see how we teach in Munich and to get to know us. Then our other guest is Dr. Thomas Maul, who is the local organizer of this program in Singapore. So, very warm welcome for you guys too. I hope you enjoy our lecture today. And I will start with a short wrap-up of last week's lecture. So, we discussed Nyquist ray digital to analog converters last week, and the last circuit I have shown you was this binary weighted current mode converter. The operation was like this. We have a set of binary weighted current sources corresponding to the binary weighting of the binary input word, of the digital input word that we provide to the converter. You can see here we have a current IR controlled by the MSB. We have a current IR over 2 controlled by the next bit, and so on and so on. If we go towards the least significant bit, we always reduce the weight of the current sources by a factor of 2. Then we collect all these currents and sum them up here in this virtual ground node of this operational amplifier. You know the input impedance of this OpAmp is very high, so the current cannot enter the OpAmp and is hence forced through the feedback resistance, where it is converted into a voltage again. Well, then we have seen that there is 2 main impairments that can occur in the binary weighted DAC compared to the other DACs that we have discussed before, which was the resistor string converters. We have seen that if there is a mismatch in the weighting of the current sources, and I showed this for one example where the current source corresponding to the MSB was too small, then it may happen that if we increase the input word by 1 LSB, for instance, from 0, 1, 1, 1 for this example to 1, all 0, then we would expect that we go up by 1 VLSB, 1 VLSB. But in the case that we have a variation here and our main current source is too small, then it may happen that we even go down. And this was this non-monotonic behavior that can occur in binary weighted converters. Please be aware that this is possible always if we have a binary weighted structure, and throughout today's course we will see countermeasures to avoid this. The other effect was that if the input signals are not switching exactly at the same time, if there is some latency on one signal path that may arise from the logic that computes these values, then we may have glitches, which means that we have either a spike up or a spike down before we settle to the final value. And here we have already seen a countermeasure, which was a synchronization register right in front of the DAC. Okay. What I want to discuss today is how to realize these current sources. Of course, you can implement normal current sources as you know them from your analog lecture. However, in this setup, it is even more simple to generate these binary weighted currents. If you look at this structure here, we have the same OpAmp with the feedback resistance, which has the purpose to convert the current collected here from all these current sources and to convert it into a voltage. Then you should note that at this node we have a virtual ground potential. So this is fixed by the OpAmp as long as the gain is high enough. Well, in fact, it varies a little bit due to the finite gain of the OpAmp, but here let's assume that we have a perfect virtual ground potential here. Then we can take a reference voltage, which is in this case minus Vref. And if we then take a resistor and place this resistor in between the virtual ground potential here and the negative reference voltage here, then we have the situation that the voltage drop across this resistor is minus Vref. And hence the current I1 prime can be expressed as I1 prime equal to minus Vref over 2R. You remember the fact that I said last time we should never disconnect the current source completely, because then we have the situation that the current source wants to draw a certain current. If the current source is disconnected, obviously the current has to be zero, and this leads to a conflict that brings the current source into an operating point where it cannot work as a current source anymore, and if we connect it back, then it requires some settling time. And the same holds here, of course. If I would disconnect the resistor completely, then this node voltage would drop towards minus Vref, and if I connect it back, then I have to charge it up again, which slows down the operation of the circuit. Hence, it is advantageous to disconnect the resistor from virtual ground and connect it to a analog ground which carries the same potential. Then for the resistor, nothing has changed. The voltage drop of minus Vref is the same over the resistor. The current is the same, and if we bring it back to the virtual ground node, we settle pretty fast. What about the other currents? We have here a current I2 prime, here a current I3 prime, and this is a current I4 prime. And of course it's pretty easy to compute these currents by Ohm's law. This is just minus Vref over 4R. The I3 is the minus Vref over 8R, and so on and so on. Finally we have the I4 equal to minus Vref over 16R. So you can see that we have binary weighted currents simply by choosing binary weighted resistors here. What about the current on the other side of the switch? Well, here we have the currents I1, I2, I3 and I4. Well, these currents are either zero if the respective bit is equal to zero, or they are equal to the current in the resistor if the respective bit is 1. So in an algebraic way we can simply write I1 is equal to minus Vref 1 over 2R times B1, and so on and so on. Finally I can write I4 is equal to minus Vref 1 over 16R times B4. And all these currents are summed together, and we end up with a current here as the sum over all In, where n goes from 1 to 4 in this case. And this gives us an output voltage V out equal to minus Rf times I, where I is this current. So we have this equal to Vref times Rf over R 2 to the power of minus 1 B1 plus 2 to the power of minus 2 B2 and so on, as we expected from a DAC. Okay, pretty easy structure. Operational amplifier with feedback resistor, binary scaled resistors, and the switches connecting the resistor ether to analog ground or virtual ground. What is important for this device? If we count all resistors in terms of R, so if we count unit resistors, then we can find in this structure we have 30 unit resistors. This is important to compare it to other structures I will discuss now. So we have 30 unit resistors. We have a binary weighted structure, which means that it is not necessarily monotonic. As discussed, there may be glitches. And the ratio of the Imax to the Imin is equal to the ratio of the Rmax and the Rmin, which is 2 to the power of n minus 1. So you can see that the ratio between the largest and the smallest resistor goes up with the number of bits. And this is a thing that is disadvantaged from a matching point of view. If we want a good matching, which means that we want to reduce the variation in this device in order to avoid this effect of non-monotonic behavior and have a good accuracy, then it is important that we keep our variation small, and hence it is disadvantageous to have such a big ratio here. We will see today how we can reduce the ratio between these resistors. Well, one technique to reduce the ratio is to say, let's simply take two DACs and let one convert the MSBs and the other one the LSBs. So this can be seen here. We use a MSB DAC and we use an LSB DAC. Well, then it is important that the MSB DAC has a higher weight than the LSB DAC, because the MSB DAC does the coarse adjustment of the output voltage and the LSB DAC the fine adjustment. So if we use the same reference voltage for both devices, they have the same weight. So it is important to reduce the weight of the LSB DAC, which can be done by saying, okay, we take the output voltage of the LSB DAC and we divide it by a factor 2 to the power of n, where n is determined depending on how we partition between the MSB and the LSB DAC. So we reduce the LSB weight and then we add it to the output of the MSB DAC. What we can also do, and which is often the same, depends on the implementation, is to scale the reference voltage. So you can see here that we add the MSB DAC signal and the LSB DAC signal without a reduction of the weight. Well, because the weight is already reduced, because we have here a scaled reference voltage. So we go down with the reference voltage of the LSB DAC. So how can this be done? Let's look at the converter we have discussed previously with a small modification. It's exactly the same circuit. What you can see, however, is that we have introduced here a resistor and we have introduced here a resistor. Then it is interesting to note that at this point we have the virtual ground potential. Here we have the analog ground potential. So from a potential point of view, these two nodes are connected. We have the operational amplifier assures that the potential here and the potential here is always the same. So this means that we can consider these two resistors to be connected in parallel. So we have 4R in parallel to 4R, which gives a resistance of 2R. And this is connected in parallel here to another 2R. So all these three resistors here behave effectively as a resistor of 1R. Okay? So we have here, if we look into this green box, we see a resistance of R. Well, here we have 3R, here we have 1R. So we have a structure like this. We have the 3R, we have 1R, and we connect this to minus Vref. So this results in a voltage at this point which is minus Vref over 4. And this is indeed the potential that we see at this node. This is minus Vref over 4. Let me go back one slide. Here we said we have the MSB DAC and the LSB DAC. And the LSB DAC receives a reduced reference voltage. So this is what we have here. We have the reference voltage for these two resistors here. They see the reference voltage. So here we get a current corresponding to the reference voltage over 2R. Here reference voltage over 4R. Here we have again 2R, but now we have the reduced reference voltage, so we also get a reduction of the current by this factor of 4. So let me clean up a little bit. You can get rid of this and this. And we can say our output voltage, V out, is equal, as for the previous one, Vref RF over R. And then we start with our first resistor here. This is 2 to the power of minus 1 B1. And the next one is 2 to the power of minus 2, this is this 4, times B2. Then we would normally continue 2 to the power of minus 3 B3, but now we have the scaled reference voltage, so we have to work with this one. So we have 1 over 4 Vref times feedback resistance over R. And now we do not have 2 to the power of minus 3 because we have a 2R here. So we have here 2 to the power of minus 1 B3 plus 2 to the power of minus 2 B4. However, if we combine this 1 over 2 with this 1 over 4, then we have again the correct weight that we would expect for the third bit. Okay? Again, the same equation that we expect for a normal binary weighted DAC. However, now we have other resistor values here. And if we do the same comparison then on the previous slide, I can say we have now a ratio of R max over R min, which is now 4R over 2R. So we have only a factor of 2. So this is reduced. And this reduced ratio is very good for matching. Well, the ratio of the currents Imax over Imin is of course unchanged. So this is still 8 because this is what we need for a binary weighted DAC. So this is unchanged. And the other interesting point, scaling the reference voltage affects all bits coming after that point. So we have now a sum of only 19 unit resistors. So this structure is not only advantageous from a matching perspective, but it is also advantageous from an area perspective. Because if we assume that the resistors take most of the area or a large fraction of the area, then reducing this reduces the overall size of the circuit and so the overall cost of the circuit. Okay. Still, we have somehow an irregular structure. We have to scale these resistors. Then at one point we have to scale the reference voltage. And for sure, if we go for more bits, then it becomes even more irregular. So the question is, can we make this structure even more regular and still produce binary weighted currents? And the answer is yes, we can. And to understand this, I want to discuss this so-called R2R ladder network. It is called R2R network because if you look at this circuit, you can see only two types of resistors. One is the R, the other one is the 2R. So let's start the analysis from behind. So we have here, at this node 4, we have 2R connected to analog ground, and we have another 2R connected to analog ground. So these resistors are connected in parallel. So effectively, they form a resistance of R. So we have here the R4 prime, which is equal to 2R. And we have an R4, which has 2R in parallel to 2R. And this gives the reduced resistance of R because we have these two current paths. So, starting from that point here, we have 2R. Then we see another R here. So, looking into the circuit at this point means that we have R3 prime equal to R, this is this one, plus the R4, which is the parallel connection of these two guys. So we have R plus R, which means that we have again 2R. And then if we go a little bit ahead, we see then parallel to this effective R, we have another 2R. So we get R3, which is 2R in parallel to 2R. And again, we have 1R. And then we can continue like this. We can say, okay, we go to the node R2 prime, which is again R, this one, plus the effective R, so we end up with 2R, and we have the R2, which is 2R in parallel to 2R, which is then again 1R. Why is this good? So we see that we have always this regular structure, and if I look from the nodes which do not have this prime tick, then we see that we at these nodes we always see 1R. So let's assume that we have the reference voltage here. Then here is 1R. From this point, we have another R. So we have 2R in series, which according to the voltage divider formula gives us at this node a Vref over 2. Then we have 1R here, and all the rest also forms 1R. So we have again 1R in series to another R, which gives us another divider factor by 2. So we have here Vref over 2, then we have R connection. So at this point we get a Vref over 4, and so on. Here we have a Vref over 8. So although we have only two types of resistors and this regular structure, we divide our reference voltage by a factor of 2 from step to step. And of course we can use this to generate binary weighted currents. This I1 is the Vref over 2R. And this one is the voltage over 2R. And the voltage now is Vref over 2. So at the end here we have a Vref over 4R. And here also voltage is Vref over 4 over 2R. So we get effectively a Vref over 8R, and so on and so on. And you can continue this structure as you want. So to generate more bits, you add more of these R2R cells. The important question is, how can we take advantage of these binary weighted currents? Because here they are flowing into a ground. So in a structure like this, we lose these currents. If we look at the previous circuits, here we collected the binary weighted currents depending on the switch position into the virtual ground node. So to do the same thing here, we have to say, well, this is not a ground node. This has to be a virtual ground node in order to collect these currents. So imagine that we take this structure and simply flip it around. Okay, we flip it around like this, and then we end up with a circuit like this. You see, we have the same R2R network. However, these nodes here we had ground nodes here, 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 and here. And we removed this ground, and now we can connect this node either to the virtual ground here of the operational amplifier or to an analog ground. So if it is connected here to this virtual ground, then we collect all the currents here and force them through the feedback resistance where it is converted into a voltage. Okay? The good news here is we have only two types of resistors, and the 2R resistor can be built by a series connection of 2R resistors. So we can build up a binary weighted current network simply by using one type of resistors and an appropriate connection of these devices. Okay. Do you have questions so far? There is another type of DAC that takes advantage of this R2R network. This one is a little bit harder to analyze. So I guess you will do this in the tutorials, Michael, or not? Okay. So then it's a good idea that you analyze this circuit over your three days. Well, this one is a little bit harder to analyze, but in principle it is again the same story, that we subdivide currents in a binary way. If we look at the very first current source, then you see that now we apply not reference voltages but currents to this R2R network. Here the first current source is directly connected to the virtual ground. So no reason for the current to flow here into this resistor network, because here we already have this virtual ground potential, so all the current flows through the feedback resistance. The next current source is connected one node ahead in the R2R network. So you know from this point we see effectively here one R. We have another R here, so we have a current source that sees two paths. One has a resistor of R, the other one has a resistor of R. So obviously the current is equally divided. So 1/2 times I flows here towards the virtual ground. And then for the other current sources, it's a little bit more complicated, but it's again and again divided. And what comes to the virtual ground is here I, here 1/2I, here 1/4I, here 1/8I. Important and useful for the investigation of such a circuit is the so-called current divider formula, and I repeat it because my experience is that it is less known than the voltage divider formula. So imagine that you have two resistors connected in parallel. This is the R1, this is the R2, and they are connected. Okay, there's no room. This is a V. They are connected to a voltage V. So this means we have a current I1 here, and we have a current I2 here. Well, the effective resistance R is equal to R1 parallel to R2, which is of course R1 times R2 over the sum of these resistors, R1 plus R2. And this gives us the voltage drop V equal to R effective times I, where I is the total current flowing here. And of course this is equal to the parallel sum of the resistors times I. So I1 is V over the branch resistance R1. So this is R2 equal over the sum R1 plus R2 times I. And the I2 is equal to V over R2, which is R1 over R1 plus R2. And this is the voltage divider formula. So if you have a parallel connection of two resistors, I is missing here, then the current is divided into the two branches according to a ratio which is given by the resistor of the other branch over the sum of the resistors. So this is similar but not exactly the same as the voltage divider formula. In the voltage divider formula you have the resistor where you take the voltage from over the sum of the resistors. Here you have the resistor of the other branch over the sum of the resistors. But it's quite useful formula that you can use to analyze circuits where current is divided into different paths. Okay. Then I want to draw your attention to a circuit we have already seen and analyzed, which was the switch capacitor amplifier. Here, if you go 2 or 3 lectures back, then you find in your lecture note the switch capacitor amplifier, and we saw that in the amplification phase, the output of this device is equal to the input voltage times C1 over C2, where C1 was this input cap here, C2 was the feedback cap, and if you remember, the C3 was useful to keep the voltage constant during the pre-charge phase of the other caps. Well, when we discussed this circuit, I already mentioned, well, can we use this one as a DAC? And the reason was that we say, well, the output voltage V out is linearly dependent on the input voltage. On the input voltage, and it is also linearly dependent on C1. So if we can make the C1 controllable, then we can make the gain of the switch capacitor amplifier controllable. So how can we make this guy controllable? Well, the easiest way is to say, depending on the control bit, we connect an additional cap in parallel or we disconnect it. And then you can do this with even more capacitors, and you can end up in a structure like this. Well, here we have a first resistor, and we can connect it here to the input. Then it is effective in the switch capacitor amplifier, or we can connect it to an analog ground, and by connecting it to analog ground, it is connected between the virtual ground and the analog ground, so it is always discharged and it is not relevant for the output voltage. And then we can do this with other caps, and we can do this even with binary weighted caps. So we have a cap of 2C that can be connected here to the input, or we can connect it to the analog ground. By doing this, we make this gain factor here controllable, because we say the C1 is equal to C times B4 plus 2C times B3 plus 4C times B2 plus 8C times B1. So by making this one controllable, we can make the gain controllable too. The interesting point is, actually we have a switch capacitor amplifier with a variable input voltage. To make this a DAC, we have to fix this input voltage, and we have to apply here a Vref. Then the output depends only on the binary control word and this reference voltage. However, we can also say we keep this a V in. We can also say we have a V out equal to a factor K depending on the V in times Vref. Or we can say the output signal is equal to this factor K depending on the binary input times V in. Now, this is a varying signal. This one is a varying signal. So we call this a multiplying DAC, because it's actually an amplifier with varying gain factor. Let me go back. Perhaps you can see it here more easily. If I dynamically vary this gain factor depending on a bit, then I multiply the output the input signal with this factor. So this is called a M DAC, a multiplying DAC. Because now we multiply the input signal with this digital control signal. Okay. So if you find such a word MDAC, then you see that it's nothing very difficult. It's strongly related to the normal DACs. The only difference is that we have here not the reference voltage but the signal voltage. Okay. Today we have seen several different implementations of binary weighted converters and how to realize them. However, what we still have is the problem of the glitches. If these signals do not switch at the same time, then we have the problem of the glitches. And what we also have is the problem of the non-monotonic behavior. And non-monotonic behavior can be very, very disadvantageous, in particular in control applications. Imagine you have a controller that says to your actuator, go up, and then it increases the input control word of the actuator, but it doesn't go up because of the non-monotonic behavior of the DAC. It goes even down. And then you can disturb your control loop considerably. So it is advantageous to have a monotonic behavior, at least for the most significant bits. So the question is, can we reuse the structures of the binary weighted converters that we have discussed so far, but make them monotonic? And the answer is yes, we can do this very easily by using a new coding of the structure. I'm missing one slide. Okay. By new coding of the input signals, which is called which is called a thermometer code. So if you look at this code, then you can see here your binary values, and we count up from all 0 to all 1 in a binary way. So 0, 0, 0, 0, 0, 1, and so on and so on. This is the binary coded way, and here we have exactly these problems of the non-monotonic behavior. Now let's translate these 3 bits, which are very compact form of information here, into 7 other bits. So let's translate this B1, B2, B3 into D1, D2 to D7. And let's do this in such a way that we say if all input bits are 0, then all output bits of the decoder are also 0. Then we go up by 1 LSB. So we have 0, 0, 1. And this translates into all output bits equal to 0 except 1. One of the output bits is set to 1. Then we go up by 1 LSB in the binary word, and you can see now we have 2 output bits set to 1. So if we count up the binary input words, we get 1 additional 1 in the output of this binary to thermometer decoder. Well, you can see this is a very inefficient way of storing or representing information, because for each step we have, and in an n-bit DAC we have 2 to the power of n steps. For each one we need an additional wire which can be either 1 or 0. However, you can see if I change here by 1 line, then I get 1 additional 1 or I lose 1 additional 1. But I do not turn on 1 and instead I turn off several others as we had it in the binary converter. Well, why is this called a thermometer decoder? The thermometer code, or the reason for the thermometer code, if you look at these old fashioned thermometers where you have here your scaler and here you have your mercury, which can go up and down. Then you have exactly the same thing here. If you increase or reduce the binary input word, then the transition between this 0 and 1 shifts left and right. This is why it is called a thermometer code. So how can we take advantage of this one in our converters? If we look at this structure, then you can see now we have only one type of resistors. Okay? This is a 3-bit DAC. So we have here 3 input bits, and this leads us to this 7 thermometer coded output bits here. And if 1 bit is 1, then I connect the respective resistor to the virtual ground of the OpAmp. If the bit is 0, then I disconnect it from the virtual ground and connect it only to the analog ground. So if I go up, then I add additional resistors. If I go down, then I remove resistors from the virtual ground. Why does this lead to strict monotonic behavior? Well, if I increase my input vert, then I connect more resistance. So I produce more current here flowing in the feedback resistor. The worst thing that can happen is that one of these resistors is broken or the switch is not working or whatever. So let's say 100% variation of the device. Then the current is not going up if I connect or disconnect this, if I connect this element. This is the worst thing that can happen. But it cannot happen that I connect the resistor to the virtual ground and current is going down. This cannot happen. So here we are strictly monotonic, similar to the resistor string converter. If you think back to the resistor string converter where we had these resistors connected in series, like this, and we said, okay, here's the reference voltage, and we use a big analog multiplexer to connect one of these voltages to the output. Well, then the worst thing that can happen is that one of these resistors is broken, is not there. So effectively I have something like this, and the voltage at this node and at this node is the same. But then the voltage increment is 0, but it cannot go down. So this is the reason why we said, okay, this one is also strictly monotonic. And the same thing happens here if I use a thermometer coding. Well, what is the disadvantage of the thermometer coding? Any idea? Yes, simply the effort, okay? You say the number of resistor increases. Well, you can see it, I guess, from this table here, that this is very inefficient way of coding things. The advantage of this binary converter was that due to the binary scaling we can get a high number of bits with only a couple of elements. Here we need for one step one element, which again means lots of effort. So this monotonic behavior does not come for free. We pay a high price by building a structure like this. Well, however, it is important that you analyze your application very precisely. And if your application is susceptible to non-monotonic behavior, then you should consider using thermometer code. If you have an application where you say, okay, perhaps it goes down at some point, but this does not corrupt my system operation, then you can stay with the binary weighted structure. And we will see that we also can combine this approach. Let me skip this one. Here, this is an example of a hybrid converter. This is only an example. There's various types of hybrid converter. And important is that hybrid means here we use a thermocode for the MSBs. And we use a binary weighted structure for the LSBs. Well, this is a compromise, okay? We say for the MSBs, for the bits that have a huge impact, there we use a thermometer code, because at least we want to avoid large non-monotonic behavior, and we want to be monotonic in the MSBs. And then you might say, well, the LSBs, they are only a fine adjustment, and here we may accept a small non-monotonic behavior. And hence we can use a binary weighted structure in the LSBs. Well, how does this circuit work? Again, you see here we have the standard OpAmp structure that converts a current into a voltage. So we have to determine the current flowing here, because this is the one forced in the feedback and converted into a voltage. So you can see that this current is the sum of all these currents flowing out of this network, so it makes sense to analyze this network. Before we do so, it is important to understand this circuit here. Has anyone seen this before? This should be known from the analog lecture. So this is what people call a current reference. Why is this? Here we have a fixed potential. And we have the operational amplifier connecting this node virtually to a reference voltage. So we have a reference voltage between this node and this supply node here. So let's say we have here a Vref. In this example, the Vref is connected between this node and VSS. So it's a reference voltage referred to VSS. This means that we have the reference voltage drop over this resistor. So the voltage is fixed, it's always the same. So the current flowing here is Vref over 2R. And how can this be? Well, the operational amplifier forces this Vref potential here. So it controls, or it does this by controlling the gate potential of this NMOS transistor such that we have this current here. Which means, if I have this reference potential here, if I have the voltage generated by the OpAmp and connect this to an NMOS device, then I get this current. So we can do this with another transistor. We can say, okay, let's take the same gate voltage of the OpAmp and apply it to another transistor. And we assure that the condition at the source of this NMOS transistor is the same as for the blue one. Okay? At the source, we have the same 2R. We have the same gate potential. We have the same dimension of the transistor here. So this means that this device sees electrical exactly the same conditions as this one. So here we have the same current flowing at this node. So here the same current of Vref over 2R is flowing. So this is nonsense. This is a 2R. Okay? This is important. We convert with the blue box, we convert a reference voltage into a reference current. And then we duplicate the reference current by connecting it to more than one of these transistors. And we do this several times. So we do this here again, and here again, and here again. So in all of these red transistors, the same Vref over 2R current is flowing. So we have here and here and here and here the same current. And then we use switches to connect this current to the virtual ground where we collect them. Here we can connect them to the OpAmp, or if the respective bit is not set, then we connect this current to an analog ground, and then the current is dissipated. Well, we have here always the same current that can be connected to the virtual ground or not. So for these wires here, so also for the respective bits controlling the switches, we are thermometer coded. We can connect a unit current or we can disconnect the unit current. But the currents here are not binary weighted. So we have monotonic behavior here. What about the last current? Well, you can see here we have also a Vref over 2R. But this one now is supplied to our 2R network. So you learned today, here we have a 2R, here we have effectively another 2R. So the current sees at this point two resistors with the same value, so it's divided in the same way. Here we have half the current, here we have half the current. So at this node we have Vref over 2R divided by 2. Then the other half flows to this node. Here again we see 2R in this direction and we see 2R in this direction, so the current is divided again by a factor of 2, and we have here the Vref over 4R. Here we have the Vref over 8R, and so on and so on. So this is this hybrid approach where we say, okay, to be accurate on a coarse scale, to be monotonic on a coarse scale, we use the thermometer code there, and to be efficient in implementation on a fine scale, we use the binary weighted structure. Several different ways to make this. This is just an example, but the idea is always the same. MSBs, thermometer, LSBs, binary weighted. Okay. Questions so far? Then let me come to another type of DAC. So far we have generated either voltages or currents. And based on this we build us up our DACs. Well, if you think back to the switch capacitor chapter, then there we worked a lot with charges. And the question is, can we also exploit the charge for building a DAC? This is one example how we can do this. You can see we have here a voltage follower. This one copies simply the voltage at this node to the output. So to understand the operation of the circuit, we have to calculate the voltage at this node, and therefore it is important to say here we have this buffer, but no current can flow here. And then we have a first phase, and in this first phase we close this switch, so we can call this a phase phi 1, and this switch connects all. If I close this one, I close all these switches here, which means that I short all caps. I discharge all caps. So then the total charge on the cap, the Q total, in this phase phi 1, the Q total is 0. And we have an effective cap C total, which is equal to the sum of all these caps, the CIs over all I's, and this is simply C. Then, in the next phase, we opened mainly this switch, and for the bits equal to 1, we connect the cap now to the reference voltage. And for all the other caps, we keep it connected to the analog ground. So what is the voltage drop across a certain cap? The voltage drop across a certain cap, let's use this one for instance. This one is Vx, where Vx is the voltage at this node. No. This is the Vx. Well, then it depends on the switch position. If it is connected to analog ground, then it's only Vx. If it is connected to the reference voltage, then we have to subtract Vx. So we can simply write Vx minus B, in this case B2, times Vref. And if we know the voltage across the cap, we also know the charge across the cap. So the charge on all caps together, the Q total, is equal to C over 2. I start with the very first cap, this is C over 2, times the voltage drop that we have just calculated, which is the Vx minus B1 Vref. This is the charge on the first cap. Then the charge on the next cap is C4 over, no, this one is C over 4 times the voltage, which is Vx minus B2 Vref, and so on. This is the total charge. The question is, what is the total charge on these caps? And if we look once again at the structure, then we say, okay, no charge can flow into the OpAmp or come out of the OpAmp. This switch is open. So actually this node up here is completely isolated. No charge can come on this one. So here the total charge cannot change. So we have still a 0 here. And if I now solve this equation for Vx, then I end up with Vx equal to Vref times the sum over all caps 2 to the power of minus I Pi. Again, what we expect from a DAC. But now based on this charge cycling on these caps. Okay. A last but very important digital to analog converter is shown on the next slide. And to understand this one, we have to understand what we did so far. So far, we generated the output voltage at a single node. So we have been somehow single-ended. We can go with these structures also for differential mode, but the basic concept is single-ended. This one here is based on differential steering of currents. What means differential steering of currents? So far we have connected, for instance here we had this OpAmp here with the feedback resistance, and we have connected a current source to this node, and this current source was either connected to this analog, to this virtual ground here, or it was connected to an analog ground here. So if it is connected to the right, then it's clear what happens. If it is connected to the left, well, then the current is dissipated simply to ground. The question is, why don't we use the current in the other switch position? And this is the basic idea that leads to this differential current steering architecture. Well, if you look at this circuit, then you can see that we have again binary weighted current sources, and if a certain bit is set, then we connect this current source to this plus node, and it contributes to the current I plus. Well, if it is the respective bit is not set, then the current source is connected to another node and contributes to a current I minus. So I have two branches, and I connect the current source either to one branch or the other one. The output signal is now the difference between these two branches. In this example, I convert the currents into voltages simply by forcing them through a resistor. So I have a voltage drop here, which is 1 over 2 times R times I plus. And I have a voltage drop here, which is 1 over 2 R I minus. Well, what is the I plus? You can see if I set all bits to 0, then no current source is connected to the blue line and the I plus is 0. If, on the other hand, all bits are set to 1, then all current sources are connected to the blue line and I get the sum of all these currents flowing in the blue line. All the currents not connected to the blue one are going to the red one. So I can say my I plus is equal to I is the scaling factor of the current sources, times B1 plus 2 to the power of minus 1 B2 plus 2 to the power of minus 2 B3. And the I minus is equal to B1 bar, which means if it is not going to the blue line, then it's going to the red line, plus 2 to the power of minus 1 B2 inverse, plus 2 to the power of minus 2 B3 bar. Well, it's simpler to say, okay, this is 2 to the times 1 minus 2 to the power of minus n times I, which is the total current. So this is the total current, I total, minus the I plus. So the I minus is what is left from the I plus. Total current minus the I plus. And then we can compute the differential output voltage. V out differential, which is then the difference between these two voltages, which is 1 over 2 R I plus minus 1 over 2 R I minus. And this is equal to R times I plus minus a constant factor Ri equal to 1 minus 2 to the power of minus n. This is the difference between these voltages. So now this is also different here. We have referred our output signal always to the analog ground so far. Now the output signal is represented by the difference of two voltages. And then the question is, where is this different? Around which common mode is this difference defined? And hence we have to calculate also the output common mode, V out common, which is simply the average value of the two voltages, V plus and V minus. And this one is equal to VDD minus 1 over 2 Ri times 1 minus 2 to the power of minus n. Or simply VDD minus 1 over 4 Ri total. Well, the common mode is the average value. So in average, half of the current flows through one resistor, so half the total current causing a voltage drop in this 1/2R device, and this is how far we are below the VDD. Here you can see the common mode is referred to VDD, and this is a disadvantage of this DAC as it is here, because we have no power supply rejection, because if we have a variation on the VDD here by noise, we see this of course also at the output. On the other hand, what is an advantage of this device? Any idea? What is different compared to all DACs that we have discussed so far? At least one should come into your mind. Well, it's differential. Okay, this is one. But there is no OpAmp. Okay? So we convert the currents simply by resistors into a voltage. So this means that we have relatively low effort, but mainly it means that we can go very, very fast with a DAC like this. We simply switch currents. If we do this in the right way, as we have discussed, then we do not change the potential on top of the current source. So very short time for settling. We just steer the current in between two nodes, and we force it through a resistor, and this makes a voltage drop here. So no need for an operational amplifier that would slow down the operation. This is a DAC structure that can be very often seen in high-speed structures or in RF structures, because we don't have this OpAmp that would slow down this stuff. However, the price is that we do not have this power supply rejection here. Okay, this is just one example that should show you that we are not always needed to have this OpAmp structures. DACs can sometimes look much simpler like this one here. And the funny thing is, the simpler the circuits become, the faster they are usually. And if you look to current publications and new results people present at conferences, then the circuits working with very low voltages or working with very high frequencies, they look more and more simpler, because all the fancy stuff that is needed for making it very precise and what has been published several years ago is often not applicable for very low voltages or very high frequencies. So the funny thing is that circuits get simpler again, but now the devil is in the detail, and you have really very precisely understand what you do and what the effects and trade-offs are. Okay, that's it with the DACs. This is a good opportunity to ask questions concerning digital to analog converters, because then for the rest of the course, mainly next year, we will focus on analog to digital converters. Okay. What kind of analog to digital converters do we have? Well, we will see that there are several techniques. The first and simplest one is counting operation, which is known in the so-called single or dual slope converter. This is the one I will discuss today, and we will start with the other ones in the new year. There is, similar to the counting principle, there is an integration with oversampling type of conversion. Well, it's usually known as sigma delta or delta sigma conversion. This is the class of oversampling converters working with very high frequencies that we will discuss at the end of the course. And this integrating with oversampling, the sigma deltas, are applicable for low to medium speed, but they can achieve a very high resolution. Well, low to medium is not true really anymore, because the latest result shows that with a so-called continuous time sigma delta converter, you can go even for high conversion rate here. We have the so-called weighted operation, and we will see that weighted operation is mainly a binary search of the output voltage. Well, this is a conversion technique. You can understand this by thinking of a question and answer session. I think about a voltage, and you can ask me questions that I answer only with yes or no. And your task is to find this voltage within n cycles, which means that you are allowed to ask n questions. And then the technique will be, you say, first question might be, is it positive or negative? And I say yes or no. And then you say, is it, if I say, for instance, it's positive, then you might subdivide the range of possible voltages in two intervals, and you might ask, is it in the upper subinterval or in the lower subinterval? And in an iterative way, you come nearer and nearer to the result. And this is what is the principle of the weighted operation or the binary search. These converters are known as the successive approximation or the algorithmic ADC, and I would also put this pipelined ADC as a variant to this binary search ADCs. We will see here that it's not necessarily only always a binary search. We can add some redundancy to the converters here in order to make them more robust. But in principle, you can understand it best if you think about such a question and answer game. Okay, this type of converters is suitable for medium speed and medium precision. If we want to go for very high speed ADCs, then we are in the field of the flash ADCs. The flash ADCs, you can imagine this as a single shot conversion. Here you have to ask n questions. With the flash ADC, one shot, one conversion, one step, and you have the result immediately. Well, you can imagine that this means lots of effort, and hence it is suitable only for a reduced resolution and a small number of bits. So the flash ADC is something that can go very, very fast, but with a low, perhaps medium resolution. Okay. What I do today is to discuss this dual slope ADC, this one. The basic circuit can be seen here. You can see here that we have an operational amplifier that is connected in this RC structure. Well, you should recognize this structure. From analog courses, we already also discussed it during the mixed signal chapter. So any idea what this is? What I mean is what this is. RC, continuous time RC integrator, okay? Well, it is not purely an integrator, it is an integrator where we can discharge the cap. So you can see here, by closing the switch, we discharge the cap so we can reset the integrator. Then we have connected, we have connected a comparator to the output of the integrator, and with this comparator we can determine when we have a zero crossing here of the output. Well, the first step is that we connect the input of the integrator to the negative input voltage. You know, the RC integrator itself is an inverting structure, hence we have an inverted input signal here. And if we assume that we start at any point where the cap is discharged, then we start at this point, and depending on the value of the input voltage, we integrate up. And we do this integration for a predefined amount of time. So we say, okay, for a constant time, T1, we integrate. And let's assume that we have another voltage which is a larger value, then we go up steeper, and after this time T1 we end up at this node. So depending on the value of the input voltage, we integrate more sorry, we come more up or less. So the height here is determined by the input voltage. Next, we disconnect the input resistor from the Vin, and we connect it to Vref, and Vref now is positive. As I said, the RC integrator is inverting. The positive Vref means that we integrate down now. So we do this now with the according to the reference voltage, and we go down here. If we reach the 0 at this point, this is detected by the comparator, and then we stop. If we look at the blue voltage, then we start from a higher value, but the rate of the voltage decrease is the same because we have a constant Vref at the input. So we go down with the same slope. So we reach the 0 later. Okay, I have to prolong this one. We reach the 0 later, namely here. And this is also detected by the comparator. So what about the rest of the circuit? The purpose of the rest of the circuit is to say, okay, we integrate the input voltage up for a certain time, T1. And then we start to integrate down. And while we integrate down, we measure the time that it takes until we reach the 0 here. So this T2 is measured. And the T1 is constant. Well, how is this measured? We have a counter here. We start the counter that counts with a certain reference clock as long as we integrate down here. So here we start the counter, then it starts counting until we reach the 0. Well, in the blue case, it takes a little bit longer, so at the end, the counter value is higher. This means that the counter value represents the value of the input signal. Let's look into the details. We can say at the beginning what we can compute the Vx. What I will do now is to describe this picture here by equations. So we say the Vx at the end of the first interval, so Vx T1 is equal to 0. This is the initial value. We start from 0, that's the purpose of the reset switch, plus the integral from 0 to T1. Well, it's a trivial integral because we have a constant value. We have the Vin over Rc times dt, which gives us the Vin over Rc times T1. Then we switch to the next phase. Yeah, we can compute Vx at the end of the next phase, which is T1 plus T2. This is equal to the Vx at the beginning of the second interval, Vx T1. And now, as the reference voltage is positive, we go from minus the integral T1 to T1 plus T2, Vref over Rc dt, which is Vx T1 minus Vref over Rc T2. A good choice of the time t1 is to say we define the t1 to be equal 2 to the power of n times the clock frequency. We will see why this is useful. If we then say, okay, the instance T2 is chosen such that the voltage Vx is 0, then we can say, okay, this equation is equal to 0, and we can solve for Vin. So we have to say Vin over Rc T1. This is this inserted here. This one is equal to Vref over Rc T2. Okay, the Rc cancels out. And we have then Vin equal to Vref T2 over T1. So the T1 is 2 to the power of n times the clock frequency. So we can say the T2 is equal to Vin over Vref times 2 to the power of n times T clock. This is what I have here. Let me clean up a little bit. No. There we are. So what is this? We have the Vref over the 2n. This is what we called so far the VLSB. Okay? So that's why I said it's a good choice to define the T1 like this, because then we get this factor of 2 to the power of n divided by Vref. This is the VLSB. So we can say that we have a T2 in terms of T clock, which is equal to Vin over Vref. And this is simply the number of cycles in the counter. This is the count value. So the count value represents here directly the input voltage in terms of Vref. This is what we have here. Well, this converter has a certain story. When I was here as a student, this type of converter was already known to be somehow old-fashioned and was one that is mainly suited for discrete implementation, and nobody built this in integrated microelectronics. During the last couple of years, this converter is emerging again. So we were already discussing to drop it from the lecture and say, well, this one is not really relevant, let's get rid of it. And the reason was that to achieve a good accuracy here, we need a very high clock frequency. Because you can see here, if we have a large number of bits, then the ratio, I guess I made a mistake here, sorry. This is the VLSB. Sorry. The Vin over the VLSB. this is your quantized value. And if you go for a high resolution, so for a small VLSB, then this value is large. And if this value is large, this means that the counter value is large, and this means that you have to wait for a long time. Which means if you want to go for high accuracy and fast conversion, you have to go for a very high frequency. And this is the main disadvantage of this converter, that is either slow or not accurate. Then during the last years, we saw that a new class of mixed signal circuits is emerging, which is the so-called time-to-digital converters, which is a kind of ADC for time intervals. By the way, I'm discussing this in the high-speed digital lecture in the summer semester, if you're interested in this. This is a device that is suitable to measure time intervals very, very precisely. And if you have something that can measure time intervals precisely without using excessive clock frequency, then this type of converter becomes interesting again. And indeed, it occurs again at the foremost conferences for ADCs, where people start to use this circuit again, not by using a counter and a high-speed reference clock, but by using this time-to-digital converters for measuring the time intervals. Okay, that's it for today. Next year we will start to discuss all these other ADC structures. We will have lots of things to discuss and to learn there. Thank you very much for attending even the very last lecture of Mixed Signal this year. Was again a great pleasure to work with you guys. I hope you can have a couple of quiet days and to refresh yourself again, and perhaps you can meet your families. I wish you a great time. Have a good start into 2011, and I hope I will see you, I think in the second week, Michael, huh? In the second week of 2011, after a great Christmas and New Year time. Thanks a lot. Have a good time.